Okay, hello and welcome to my channel. Today we're gonna talk about the Parseval identity and Parseval theorem. So let's start with the probability density, which is psi of x squared dx. I'm gonna write this as star psi dx. And if we put this into the k-space, you would get something like um, dk. This guy would be different. So this guy is k prime, dk prime, and you get that one squared up, and the exponential part is k minus k prime, is it? Yeah, it is. It is this dx. And you have something like this when you put this into the k-space. And as you can see, this guy right here, we did this in the momentum space lesson. This guy is the Dirac delta function, but for k. So this is the Dirac delta function for k. You can just put it away. Do like the momentum space lesson. So this guy is and the direct delta function, and as I said before, it has a shifting property to pick specific points, and it will do it right here. It will pick k prime to equal k, and thus making this guy, this would make this guy to be equal to the dk. Yep. Since these two are the same, we merge the integral and this. Oh, I forgot the complex conjugate there. You would get star phi dk. So all in all, you get this to be equal to the x counterpart of it. And from here, we got the Parseval theorem, which states that the probability density of x equal to it in 5k. And now, you're gonna ask, what about momentum? So let's try to put it in momentum space. So now, right here, P is gonna equal to h bar k. dp is gonna equal to h bar dk. And yep, and your phi of k, we're gonna put it to a phi tilde of p. Alright, and from this, you can do the Fourier transform as you did in k. So let's start. You're gonna get your psi of x would be 2 pi integral dp over h bar. Remember that part? eipx over h bar. And you can see that part is kind of weird there. Got an h bar that needs to be removed. 2 pi x x h bar psi of x. And here is where the problem began. You can see that below the dp there's an h bar. And we wouldn't want that there to secure the symmetricality to secure the symmetricality of these two guys. So what we would do is that we would want the probability density of your phi tilde. This is phi tilde. Your phi tilde to be equal to the probability density of another function of p divided by h bar. Therefore, we would put phi tilde as something of p divided by root h bar. So p tilde have to go to something over h bar, root of h bar, to secure that this thing is gone. And it would be normalizable as well. And as you can see, if we do that, we get a root h bar over here. So therefore, our x is now equal to 2 pi h bar root dp e by px over h bar of psi px. I forgot to put the function here. Sorry. And as you can see, as we do this, we will get this. And therefore, solve the question that we made in the momentum space lesson about this mysterious h bar that seems to appear out of nowhere. So yeah, this is it. You also get Parseval theorem also applied to the momentum space. So the x is also equal to psi dp. These are two different things. Don't get that mixed up. It also applies for your momentum space. And that is the probability to find the particle with momentum p in the interval p to p plus a small change dp right here. Yep, and that's it for today. Goodbye.